Greetings, everyone, and welcome to our final AP Calculus review session for the 2019 AP exam, at least. We've had 5 wonderful sessions, some of which were hosted by the incomparable Mr. Passwater from Lebanon High School. And it's my pleasure to round out our final one here. My name is Tony Record. I teach at Avon High School, which is just a high school west of Indianapolis, Indiana. And we've sort of had a lot of luck with this growing over the past 2 weeks. You know, we have a few kids here live. Most of them are from central Indiana, at least. We got a few from along the Ohio River at Madison Consolidated Schools. But we also understand that we have several of you that are watching this sort of tape delayed, right? Maybe you're watching it the following day or the day after that. Hopefully you're watching it before Tuesday, May 14th, because that would be helpful. But we really appreciate you, and we've had several, wonderful feedback, from all of you, and we've had kids watch this from California to North Carolina. That has given us some really tremendous feedback. So we thank you. We thank you for all that. I am going to close out the opening slide, and I'm going to share, if it will let me, our session today. Which is, let's see. Main screen. Okay, having a few glitches here, but I think we got it all worked out. Working 2 monitors and a lot of stuff going on here. If you come in, I'm going to try as best I can, but I will have to mute you when you do come in, because if not, this will be an absolute train wreck of sound, and it will be very difficult for anybody to hear anything. But if you think about it, as you, those of you that are just coming in, if you could mute yourself, please. And I'm going to go ahead and move on to what is our first page. If you were able to download the packet, we're going to talk about volume first of all. And the volume that I'm going to talk about specifically is not just going to be regulated to volumes of solids or revolution, but I'm going to also talk a little bit about our wonderful cross-sectional volume. Now, before we start with this, there's something I want to address. I've got 2 different kinds of volumes. I've got this thing called traditional volume. And these are the problems that are just a little bit old. They've got a little bit of age on them. You can see that this is 2014. Well, that may not seem old to maybe Mr. Passwater or I, might seem kind of old to you guys, but this is kind of one of the last of the dinosaur volume problems that seem to have gone extinct a little bit. Ever since the redesign took place in 2017, we've seen a different type of volume problem. Now, that's only on the operational exam. That's the exam that students within the United States have been taking. That's the exam that, of course, you are all going to take next Tuesday. But as some of you may have recognized, if you've taken any of the international practice exams, some of these traditional volume problems are surfacing on those particular assessments. So it's kind of difficult to tell. Are we going to see a traditional volume problem this year? It's been a few years. Certainly we're due for one, but maybe we might see a more contextual type of volume, and I'm going to show you that particular problem as well. So a lot of the free response questions that we talk about today, because we're focusing on one type of concept, I may not do every single part, but if I don't, I did make sure that the packet that you were all given access to does have the scoring standards, so that if you wanted to work any of the problems that we don't do, you will have a means by which to check your answers. So we're going to take a look at 2014 AB2. It reads that we have R as the region enclosed by the graph of f of x, which is equal to this quartic function, and the horizontal line y equal 4. Notice that they're shown in the figure. Things aren't partitioned along the x and y axis, so we have to trust, of course, that this value up here indeed is going to be 4. The problem asks us to find the volume of the solid generated when R is rotated about the horizontal line y equal 2. Now, I don't really have a lot of room down here to draw in y equal -2. I also want to do as good of a job as I can. but I'm going to use a dashed line to denote this axis of revolution down here. And oftentimes you might see textbooks or teachers use the little swoosh symbol to denote that we are going to revolve. Now, the next thing that we are going to do is think. We are going to think for a moment. I'm going to go back a slide here. I'm going to introduce or reintroduce, hopefully, a couple of formulas that you may have discussed in your class. These are the two main formulas that center around volumes of solids of revolution. And we have what you hopefully remember to be the disk method. And then you have the washer method, which is the second one. And it's very easy for students to get these two mixed up. They sometimes often have a difficult time recognizing which of these two formulas that you're going to use. And really the crux of the two formulas, without going into tremendous amount of detail, are just that these are using the volume of a cylinder. If you think about the volume of a cylinder, which is pi times the radius squared times the height, we actually have those components. Obviously, the pi is pretty self-explanatory. I think we could construe that this r could stand for radius. We are squaring it after all. And this dx is going to serve as the thickness of that particular disk, which if you tilt your head sideways, that disk that has this wee bit of thickness looks like a cylinder. And this here makes up that dx that we talk about. Now, if we return to our problem, we can see that this axis of revolution and the shaded region has a little bit of space in between it. And to emphasize that a little bit, I'm going to color this in. Now, keep in mind, I'm using some highlighting materials and so forth, and you're not allowed to use a highlighter on the AP exam. But if you feel the need that you would like to shade in a region such as this, you could certainly use your pencil to do that. So you can see that our region R is a little far removed from our axis of revolution. And that's an indicator that we are going to be using the washer method. We are going to have a hole in our revolution, so to speak. And what I've always told my students is that if you can set up a couple of representative rectangles, you're going to stand a much better chance of being able to answer these kinds of questions. Sometimes I'm a little rough on my students, and I kind of refuse to help them if they don't set up the representative rectangles. I know a couple of students in here can attest to that. But it turns out that I never hear back from them, because if they do set up the representative rectangles, it's very, very likely that they were able to solve the problem correctly. So to set up these so-called rectangles, what I'm talking about here is simply using a rectangle that will start from the axis of revolution. Let's use the better pen here. So it's going to start right down here, and it's going to go all the way through the first boundary. That would be the curve, the f of x curve, and it's going to go all the way to the top part of the shaded region. And this is the rectangle that is the larger of the two that I'm about to draw. This is going to be called R, or R of x. Now, I know it's a little confusing because I'm calling this thing capital R, and we already have the shaded region that is being referred to as capital R. I don't think that that should be a problem. You know, they're two totally different ideas. In fact, we're not going to really refer to the R in the shaded picture much more unless we read some more of these upcoming parts of the problem and it asks us to use the shaded region again. So if we go back to our little cloud here, the washer method says that we will need to take the length of that capital R and square it, and then we'll have to subtract it from a length of a little r and square it. Well, let's go ahead and throw in that little r. So if we return to the picture, the little r is going to be another representative rectangle that will emanate from the axis of revolution, and we will take it to the near side of the curve. Kind of makes sense if you think about it. Capital R is a little larger than little r. Literally, that's kind of true. So now we have the building blocks by which we can set up our volume. So we're going to go in and we're going to go ahead and think about volume equaling pi, which is part of our formula. Now, some students might, and some teachers for that matter, might talk about finding our boundaries or limits of integration first. You certainly are welcome to do that. I'm going to cross that bridge when the time comes. Doesn't really matter how or what order you assemble this particular expression. I've had success doing it both ways for many, many years. So we're going to go ahead and put this integrand together. So the length of capital R, well, there's two ways to do that. One way is just using some basic intuition, and if it allows me to kind of take this R and move it side to side a little bit, the whole rectangle is not going to move, obviously, because I didn't draw it in the correct timely fashion. But no matter where I put this rectangle, it seems like it's always going to have a constant length. And we can think of the fact that, well, it's 4 units above the x-axis, and then we got 2 units that go below the x-axis, so that seems logical that it's a total distance of 6. And that is very much the case. But I'd like to tell my students to think about it a little bit more, maybe less intuitively, but a little bit more along the lines of algebraically, because we're not always going to be lucky in that we have rectangles that have the constant width. So I have a very common mantra in my class that says we always take the top, subtract the bottom, in that order. Top minus bottom. I bet we say that phrase at least 50 times throughout the course of the week that we study areas and volumes and whatnot. So if we take the equation of the top of this particular shaded region, which is denoted by the function 4, that's going to go first, and then we're going to subtract the bottom, which is our -2. And you can see how that's going to eventually become 6. And yep, we are going to square that down the road. And we have now figured out our capital R. So we've got this much into our setup. Now we subtract the little r. So I'm going to go ahead and return, throw in our minus sign, and then to find the length of the red rectangle, little r, we do the same thing. We are going to take the function. I really don't feel like writing this function out again. We saw that a lot in the rate in and rate out seminar last night, where you can just basically name the function f of x, and then we will subtract the bottom, which is a minus -2, and all of that will be squared as well. And then of course, we're going to integrate this with respect to x. Tell my students, if you're ever confused if you're going to integrate with respect to x or y, just take your finger and your thumb and size up the width of this rectangle. I would really love to show you this, require I turn my camera on, and who knows what can happen with all of our bandwidth. But just picture me looking at you right now through the computer and holding up my finger, right? My finger and my thumb. Well, that looks good, doesn't it? And in between my finger and my thumb, I'm measuring this. And because this is a horizontal distance, we can construe that as a change in x. We have this integral set up with respect to x. Yes, you could have simplified these double negatives to call them positive. That's not a problem. But we have one more obstacle to overcome in this particular problem, and that is to figure out what its boundaries or limits of integration. Now, it seems logical, or it might seem possible from the picture, that the left boundary is 0. I don't know if I would necessarily trust that, because there is just a little bit of thin sort of correspondence between the curve and the horizontal line. But I think if you were to very quickly set f of x equal to y, you can see how very possibly 0 is going to be a solution. And I think we'll take a look at that via a calculator here in a little bit. If you just subtracted 4 over to the other side, the 4s would cancel, and then you're left with this expression equal to 0, at which point you could factor out an x and get 0. So we're going to go ahead and just assume that maybe 0 is a lower boundary, and if it's not, we can definitely change this. We're going to use the calculator here in a bit. All right, this is problem number 2. But this guy over here, whoops, not that guy, this guy over here, sorry, has got me a little concerned. That thing there is a little bit trickier because I don't know if it's going to be pretty or ugly or what's going on. So we're going to go to a calculator, and now this is a bit of a challenge for me tonight because I know that I have a little bit of both of you. I've got some TI-84 people and I've got some TI-Inspire people. So I'm going to try to give both calculators just a little bit of love. So I'm going to switch over here to the TI-84 where I've already got the 2 functions typed into my Y1 and Y2 entry lines. And then if I go ahead and let's go ahead and graph these. I know I haven't got my window set, but I'm just going to just take a chance here and graph and see what I've got. That was a bad chance. Never graph, right? Always hit zoom standard first, especially when you're graphing something complicated and it takes a while. So let's go zoom standard. And I'm going to go into my window because something is not going well here. Yeah, zoom standard. How come zoom standard didn't work? Oh, because I hit zoom 5, I hit zoom square. There, zoom 6, zoom standard should work. There's my graph of f of x. Pretty soon there's my graph of y equal 4. So we can go ahead and find the intersections of these two graphs pretty easily. We can go into I believe it's in the second trace. You have to forgive me, I'm a little bit rusty with my TI-84, but we can calculate the intersection of these two curves. And then, like you saw yesterday, you're talking about two curves that are only existing on your screen, so you can just cycle through the enter, cycle through enter again to get to the second curve. And as far as the guess is concerned, the closer you move your cursor to the point of intersection, the fewer nanoseconds that it's going to take to calculate, and you're not going to really be able to notice a difference. So if I choose that as my guess, yes, it turns out that x equals 0, y equals 4 is one of my intersections. It's just what we thought. But it's this other intersection that we're a little bit more concerned about. So we'll go into second trace again, compute intersection 5, and then our first curve doesn't change, our second curve doesn't change. Now on the guess, you want to make sure that you get this cursor closer to the second point of intersection, because it's always going to gravitate towards the intersection that is closer. There's an algorithm built into the calculator that knows which direction it's going to go. So I would probably be safe right there, but you know, I want to save you guys a few more nanoseconds, so I'm going to get a little closer, and eventually I will get an answer of 2.3 for my x and 4 for my y. This might seem a little scary to see that 2.3, and you might be thinking, hey, do I need more decimal places here or not? And you're fine. This is a terminating decimal. The TI Inspire and the TI-84 innately are going to be set to give you a few more decimal places if this were going to be taken out beyond the tenths unit. Real quickly on the TI Inspire, with this one, you can do so many different things. It's just, you know, take your pick. I mean, we could call the first function f of x. I could call the second function g of x. I could go ahead and define it to be 4. And one of the neat things about CAS is that you could just physically say, hey, I would really, really like to solve f of x equivalent to g of x for my x. And yes, it gives you the nice answers, which is wonderful. I'm going to hope that my TI Inspire users out there are pretty adept with being able to do the graphing. One thing that you may or may not know is that if you do happen to go to a graphing page, I'm just going to add a page here. We'll make it a graphing page. One thing that you certainly can do is in the F1 of X menu, if you used, and I've already forgotten what I called it, f of x is the quartic, g of x is the line, you could go ahead and just rename f of x, f1 of x, to be the f of x, and it knows what you're talking about. And yeah, it probably is just as quick to type 4 as it is to do anything else. So let's see, why is that wanting to like disco dance on me here all of a sudden? So can I type 4 in before it flashes away? Ready? Ready? Nope, didn't want to do it. All right, so we'll hit tab. There we go. So we're going to let that guy be 4, and you pretty much see the same thing. I guess one of the nice advantages maybe with the Inspire, if you're going to do the analyze graph and you're going to do an intersection, is that that's not good. Let's try it again. If we're going to do this intersection, we see lower bound at the bottom. We can just slide this across. And what it's going to do, it's going to pick up both of them at the same time. Now, they both won't appear on the screen simultaneously, but you can at least do a cursory sweep and see what's happening. Now, I don't really recommend doing this for UTI Inspire users because it's very likely that you may see more decimal places beyond 3. And at that case, you're going to want to hit enter so it locks it in, and then you can move it around and do all sorts of things with it. So anyhow, two different ways to find the intersection point at x equal 2.3. Now, one thing that we could do is we could define A or B or whatever variable name you want to give it to be that 2.3, and we could use that particular value as the upper boundary there. Once we're here, we are all set to do our integration work. And the integration work will be typed into the calculator. It's going to be fairly simple to do. I don't want to show it for both calculators, and I'm going to assume that both our TI-84 users and TI Inspire users are somewhat comfortable with this. You would just simply make very liberal use of your Math 9 for you TI-84 users. But once this is typed in and entered, you should get 98.868. Now, if this is a problem and you would like to see a little bit more detail about how this would be entered, I don't know what's going on. I'm ashamed of that penmanship there. Mr. Passwater knows that bothers me, but we're having a little lag here and it's very difficult to write. But there we go. And what I was getting ready to say is there's so many things I want to get through tonight. There's basically 4 ideas, and I don't want to carry you guys over an hour. So if there's some issues that pertain specifically to the calculator, I can certainly stay on beyond 9 o'clock, and I can share screens with either model with you. All right, we do not need a label with this problem because it doesn't mention any dimensions within the problem itself. I did kind of have a picture over here about what's happening, although it's a static still picture. If I've got this up, there's a website that I like to use. I use many different kind of Java applets. This one's kind of cool. It's called Shodor, and not to be confused with Hodor, who is a completely different and now dead character on Game of Thrones. But we have those 2 curves sketched, and what we can do is just go into this little revolve mechanism here. And let me move some stuff around. And if I hit, let's do this slowly and let's revolve this guy, it's going to slowly generate this solid that we are looking at here. And once, and possibly if it finishes, normally it's not this slow, but when you've got so many applications up. But anyhow, once this finishes, we're going to be able to spin it around a little bit and do all sorts of fun stuff with it. It's not important that a student sees this. This is certainly more of a teaching tool. It's not something that you need to have a very adept knowledge with going into the AP exam, because you're just going to find volumes of your solids no matter what they look like. But I want you to kind of see the hollowness here. Once this finishes, hopefully it does before the AP exam, and I think we might be good. So now I can spin this around a little bit and you can sort of see that hole inside. If I can get this at just a perfect angle, you can see sort of the curvature here, and we can see that shape that we've created is indeed this outer shell type of thing that happens to have that. Well, what do you know, guys? The volume is 98.86 there. So, all right, let's go ahead and talk about another type of volume here in part B. And it's also a volume that you will very, very likely run into on the AP exam. And then we call this your volume by cross sections. So in this case, that same region R is the base of a solid. For the solid, each cross section is perpendicular to the x-axis, and we have isosceles right triangles with a leg in the base R. Find the volume of the solid. Now, I know what I did here in the picture is certainly not akin to what shape we are drawing, an isosceles right triangle. But I kind of wanted to talk about how squares are sort of home base. Squares are typically going to be the easiest shape by which you're going to find your volumes, because everyone knows the area of a square is just side by side. So if you just figure out what the length of the side is and you multiply it by itself, you can just integrate that, and essentially you're stacking many of these squares together. Now you have to kind of understand that these squares are coming sort of at your face. So if this is your face, there's your face, everybody. There's your face, and you're looking this direction, that's sort of what's going on. Now, we're not talking about using squares here. We're talking about isosceles right triangles. So what I've got here is a page that could be very powerful. It could be a very beneficial way for you guys to save some time on your impending cross-section. And I understand that this particular page is not in your packet, but I would leave this up here long enough if you guys want to grab your phones and you could take a real quick screenshot of this. But you can see how, like I said, home base being the square just simply means that you're going to integrate the side of the square, which is once again our good friend top minus bottom squared. Now, don't worry so much about this with respect to A. I know in this particular problem we're talking about, with respect to our x-axis. All right. Now, each one of the other shapes that you can encounter, which could be anything from maybe not likely an equilateral triangle, it's a little bit more complicated. We could certainly see isosceles triangle with hypotenuse and a base. What are the chances of seeing a right triangle that's isosceles with a leg and a base? I would say on the 2014 exam, it was pretty good because that's exactly what we're dealing with. We could see semicircles. We could also see our friends, the rectangle with a constant height and the rectangle with a variable height. And as much as I would love to go into innate detail with each one of these, that could be a broadcast all to its own. But you can see how if a student has a rudimentary understanding of some of these coefficients, they can always take it back to home base and use the square setup. Now, the only exception to that is a rectangle of variable height, where that height C is probably going to have some kind of, variable in it. So he would have to be within our integrand so that we integrate him as well. But some of the things that I like to show students is pretty intuitive here, that if you look at this square, that I can call that length S, and say that's the piece that's in the base, that's in the shaded region. Well, if I take a look at the blue square, let's put its leg, or one of its legs, in the base. We find out that it is truly 1/2 of the area of the square. Let's take a look at the isosceles triangle. Wait a minute, this should be green, right? Should I call this green? Can I make this green? I would be happy if I could make that green, but you know what? I'm not going to worry about it. If I can't make this green, I'm not going to spend another minute with it. Oh, there it is, it's green, so it kind of matches. So anyhow, I'm going to take this green guy, and if I place this guy up here where it looks like the hypotenuse, would you agree the hypotenuse is in the base? You can see that all I've got is really 1/4 of the overall square. So a lot of times when I show this to my students, they're able to memorize these two values very, very quickly and make good use of them. For the semicircle, pi over 8 is a very, very helpful tool. And for those of you who may have taken one of the recent practice exams, you indeed had a semicircle as your particular cross-sectional piece. So I'm going to go ahead and leave this page and just realize that we are dealing with the right triangle with our isosceles nature, where a leg is going to be in the base. So we're going to use the 1/2 multiplier. So we're going to go down to our setup here, and we are going to proclaim that our volume is just the antiderivative, or the definite integral, from 0 to our good friend 2.3, and we just would take 1/2 multiplied by the quantity 4 minus the function. Because I'm going top minus bottom, we might want to talk about this, but top minus bottom just within the shape would be 4 minus the f of x. And then all of that, of course, would be squared. Okay, and again, don't forget, this is a graphing calculator problem. So at this point, you could just enter this into your calculator. It's likely that you would have f of x already stored. And so you type away the buttons and you get 3.574. And of course, some of you like to add more decimal places, and that is completely fine. All right, you can go as many as you want, because we're going to stop looking right after this. Right? The big joke at our school is you could write 8675309 over and over and over again, and you would really make your reader's day. But we're not going to look at those. We're not going to even consider those. All right. Once again, if you have a question about how to use the calculator, go ahead and post that in the chat, and we can talk about that later on. All right. So let's go ahead and move on to just a very quick peek at part C, because I did not plan to do this problem in its entirety, because it does involve area, but I still want to show you something that's very important. I want to go ahead and show you the solution. So in this particular case, you've got this vertical line x equal k that's going to divide your region R into two separate regions. So you're going to write but do not evaluate an equation that will involve an integral expression that will give you that value of k. So the problem is, we don't know where k is. K could be anywhere. K might be right here for all we know. So let's say that's our k. But what we do know is that these two shapes are equal to each other. So as you can see, there may be more than one approach to this, and I'm going to jump right again to the scoring rubric here, and we're also going to talk about the points distributed for the previous two problems in just a moment. But one way that you can do this is just to focus on your top minus bottom for your normal area, start with your lower boundary of 0 and go to that elusive k, and then just set that equal to another integral that just picks right up where it left off at k and takes it to 2.3. That's certainly one way to do this. There is another way, and perhaps some of you were thinking to integrate from 0 all the way up to 2.3, which is going to give you the entire area. But as you can probably surmise, that's going to be twice as much as what you want in this particular situation. So you could set that equal to twice. Well, take your pick. I guess either one of these would work. Because you're not going to evaluate this, it really doesn't make any difference. Even if you were to evaluate it, you're going to use a calculator anyway. So it, again, makes very little difference. So I'll just pick the first one. And that would certainly work. All right, and if anyone is thinking, yes, this would be another way to do it. That would work as well. So as long as you have an integral expression in your equation, you're going to be fine. Now, if we go back to the previous two problems that we just did, you can see that that first one with the volume of solid of revolution is sort of at a premium. Anytime on the AP Calc AB exam you encounter a single part free response question that's worth 4 points or more, it's first of all very rare, and it's pretty much a gold mine. And you can see that the integrand is very much a premium, because in order to secure these 2 points, you're no doubt going to have to set this up as a washer method. It's going to be a very egregious mistake if you set it up in any other means besides a washer. So, all right. I'm going to go ahead and stay on the topic of volume. Some of you might have a wonderful relationship with 2016 ABBC5. It's the infamous funnel problem. It's one of the last times, in fact, I think if I recall, Mr. Passwater, it is the last time that a volume of a solid of revolution appears on a free response operational exam. So we're going to focus on part B for this question. All right. Once again, I love part A. I think it's a great question. It's something I certainly would entertain, or like you guys to entertain kind of looking at, and you can check it with the solution guide. But in this particular part, we want to find the volume of this funnel. And it's amazing how many students just looked at this and thought, what the heck? It's not a solid of revolution. It's a funnel, right? It's just a funnel. Well, if we think about this just a little bit, you know, you could all like take your computer screens, and if you could, take your computer screen or your phone and just kind of tilt it 90 degrees for me, if you would. I'll wait. Okay, if that's too complicated, maybe I'll do this for you. How about I tilt it instead? So if I tilt this over just to the right by 90 degrees, all of a sudden, I think we have a new take on this problem. I think we can look at this as being perhaps an axis of revolution. Maybe we can think of this curve right here, maybe I'll draw it in blue, as being a function, you know, like an f of x. And all of a sudden, this r is really nothing more than that radius that we talk about. And I think the thing that really bothered students about this problem is that it wasn't sort of contextualized in the nice XY coordinate plane, like we're always used to seeing. But yet, when you look at the setup and the scoring standard, it's really not that bad, because we know that volume is just simply pi times a definite integral that consists of the radius squared, because this is certainly not going to involve a washer method. If I were to shade in this region here, the region bounded by the curve, and let's call it the h-axis right now, once that's revolved, that's going to make this funnel shape. So there's no sort of empty white space between our shaded region and the axis of revolution. So in some ways, this problem is actually easier than the one that we just solved, because we're just simply going to take the function, which was 1/20th, it's right there. In fact, I don't even have to write the function, but because this is a non-calculator problem, I'm going to have to do a little work with this. So if we have all of this squared, you want to make sure that that 1/20th is squared, because he is, after all, a part of the R. I can integrate this with respect to, well, let's be honest, we're not living in the XY coordinate plane. Unless you guys know some multivariable calculus that I don't know, you probably ought to let this guy be h. You probably ought to let him match this variable. And for that matter, you probably ought to make sure that these boundaries are in terms of h. And it just so happens that we have a nice set of boundaries right there, from h equals 0 to h equal 10, because the stem of the problem said that the funnel was 10 high. So that's what we've got for our boundaries. Okay. Now, in the interest of time, I'm going to go ahead and I'm going to kind of fast forward here to the scoring rubric, but I'll take my time if you guys want to write down the information. So if we go to the rubric, all right, pretend like you don't see part A, because that's your homework assignment tonight. But here's our part B. And you can see that we've got our wonderful setup right here, right? The integrand alone there is going to be worth a point. Now, because this is problem number 5 from that particular year's exam, we did not have the luxury of using a graphing calculator. So we do have to kind of entertain the arduous task of squaring all of this value. So the 1/20th is going to become 1/400, and it'll join the pi. And then if I take 3 plus h squared squared, it's going to expand into this trinomial. And, you know, for those of you who, you know, think that this is a sign of weakness, physically writing out 3 plus h squared times 3 plus h squared in order to be able to successfully compute this expansion, that is not weakness. I think that's a sign of being very smart and very careful. All right, I don't care if you draw arrows, right? Trust me, Mr. Passwater and I both have seen students do things like this. All right, you do whatever it takes for you to get the problem right. There are no style points on the AP Calculus exam. So once we have achieved this trinomial through that expansion, we can then just integrate it term by term, because it, after all, is a pretty easy polynomial. And by the time we've done that, we've earned our second point. Unfortunately, we're not quite over the hill yet, because we do have to plug in our boundaries 10 and 0. And it's kind of interesting that it looks like it might be prohibitively impossible to whittle down to a succinct numerical answer. It's really not as bad, because this 100,000 over 5 is going to cooperate nicely. But as I have told my students, and I believe Mr. Passwater has done the same, we can just leave it like this and we will be completely happy. The readers will know without question that that is acceptable, and we'll be fine. All right. So that's what I mean by a slightly non-traditional volume of revolution question. You know, we would love to be able to tell you exactly what you're going to see. I've been burned so many times. I've made predictions and they've been so far off base. We just know that there hasn't been a traditional volume question in at least 5 years, and there hasn't been a contextual volume question since 2016, so that would be 3 years. It's maybe easy for us to say that we're due for a volume of revolution. I would know and be comfortable with both approaches. All right. Part C, you got maybe another piece of homework assignment here today. This is a really good related rate question. And I would invite all of you just to spend a little bit of time with this between now and Tuesday. I thought about adding related rates into my miscellaneous topics. I did take some voting among some of my students and some students from a nearby school that I'm in contact with their teacher a little bit. And I wanted to get sort of a diverse cross-section. I didn't want it just to be Avon students. But related rates actually came up fourth, and I really thought I only had time to really demonstrate 3 topics. But please take a look at this, and if you get stuck, you've got a wonderful scoring rubric here that you can kind of verify it with and see how many of those points that you can earn. All right, what I want to do in the time that's left here is talk very quickly about L'Hopital's rule. L'Hopital's rule has now been added to the AP exam curriculum for AB beginning in the year 2017, and this particular problem is very new, as you can see. 2018 was just last year, and I want to jump right to part D for this question. So in this particular problem, we were told that a function g is differentiable, and that g of pi over 2 is, I'm going to mute some people there, that g of pi over 2 is equal to 0. The graph of g prime, which is the derivative of g, is shown below. We are asked to find the value of the limit as x approaches pi over 2 of f of x over g of x, or state that it does not exist. Now, we don't have the f of x here on the screen that you can see, but if you flip back a page and you look at the stem of the problem, or if you just look at the top, you see the f of x. So I'm going to write that here so that I don't have to scroll back and forth a bunch of times. So here's our f of x. So we look at this, and what I've been telling my students is that if you happen to come across a limit question on the free response, you can bet dollars to donuts that it's probably going to involve using L'Hopital's rule. Now, we all might feel like we know L'Hopital's rule quite well, and I think you've probably been told the nuance that we need to present with it, but we can't even get a point for L'Hopital's rule unless we make sure that we communicate that the limit of the numerator as x approaches this target pi over 2 is equal to something that's going to create an undefined value, like or an indeterminate form, I should say, sorry, like a 0 divided by a 0. And if we do this, we can quickly see that this cosine of pi over 2 is certainly going to create a 0 value, because the cosine of pi over 2 is 0, so it doesn't really matter what we have over here. And if we do this again with the g of x function, we see that, well, up here they kind of say that g of pi over 2 is 0, and we have this really fuddy way sometimes that we can evaluate limits, that even though limits are more about the journey and not the destination, very often we can plug that destination into the function, and we see up here that g of pi over 2 is 0, and we could plop that down. Now, before I go on, we got to talk about something here, because this isn't always going to happen. Let's say that we have a situation like this. What if g of pi over 2 is 0? Okay, I'll give you that. Let's say we've got that. Is it possible that the rest of the g function could look like this? What do you think? Well, I don't think that that can happen, because g is supposed to be differentiable, and that's a little problematic here. But I see how this limit, and by the way, your presenter here is having some issues, because this should not be the y-axis. How about that? How's that for a save, you guys? That's like the save of the year there. That's supposed to be pi over 2. Our x is approaching pi over 2, I'm sorry. But anyhow, we've got a situation where this is not going to work. You know, we've got to make sure that this part of the graph up here is basically living down here in order for this statement to be true that they said in the problem. And the only way that we can make that possible is by saying that g of x is continuous. Now, the reason why we know g of x is continuous is because the stem of the problem said that g is a differentiable function. And this was a very, very difficult point to earn. I graded 1,300 of these particular exams, I had 3 people say this out of 1,300. So, you know, and unfortunately, those 3 people made a mistake in another part of this problem, and so I did not see an entire 9. I saw a lot of 8s on this question. So one of the things that we want to convey to you is that if you're given the fact that a function is differentiable, there's really nothing wrong with you saying that that function, name it by name, g, is continuous. Let's be honest, you may very likely not earn any points for it, but you certainly haven't said anything that's incorrect mathematically. So once we've made that determination, then we can go ahead and all systems go for L'Hopital's rule. So that means L'Hopital's rule, we are going to take the limit as x approaches pi over 2, and we're going to take the derivative of f of x. Now, in this particular problem, that derivative had been taken in a previous part. So I'm going to have to recreate that really quickly with the product rule. So I would take the derivative of e to the x times the cosine, and then normally I would add e to the x times the derivative of cosine. Well, the derivative of cosine is negative sine, so I'm going to replace with that. All right. Now, at this point, we're going to go ahead and we are going to divide by the derivative of g. And the derivative of g of x, well, that's, well, we don't really know what g of x is. I see a graph here of the derivative of g, so I think I might have to just call that g prime for right now. Well, as it turns out, you're going to be able to evaluate this and finish it up because we can directly substitute our pi over 2. Remember a moment ago we talked about how the cosine of pi over 2 is 0, so that's going to wipe this term completely out. And then over here we're going to have negative e to the pi over 2, and then the sine of pi over 2 is obviously just 1. Now for our denominator, g prime of x, that would be the derivative function that we have graphed, and at pi over 2 we notice, oh, there is a very nice wonderful y value up there of 2, and so we'll place 2 here. Now one thing you want to be careful of, a lot of students will look at this and say red alert, this is a sharp pointy point, so that means this thing is not continuous or not differentiable, I should say, and that's not the case. G prime at that value pi over 2 is 2. There's nothing that's going to refute that. Now g double prime of pi over 2, totally different situation. That's a conversation for another day because that certainly does not exist, and you're going to have to pretend that this is a 2. All right, that would not exist. All right, so we have our solution there. And as you can see, if I jump to the scoring rubric for this particular problem, we find that it was worth 3 points. And you can see that that whole aspect of g being continuous at x equal pi over 2 was important. And if I go back to this, I'm going to rescind my g is continuous. I think it's very, very, very important that we state where it's continuous. All right, maybe we awarded points for students that just said g was continuous. But let's go ahead and hold you guys to a little bit higher standard here. If you're working with an isolated point, let's mention that that's where our continuity happens. If you're dealing with an interval, like we might see here in a little bit, let's go ahead and mention that interval over which the function's continuous. And then the rest of this, awards a point for applying L'Hopital's rule, which is pretty much what's happening with both the statements of the two separate limits equivalent to 0, and then actually taking the derivative of the top and the bottom, and then just basically evaluating that particular limit to get your answer would be your third point. Please note, it really doesn't make any difference what order you write these things in. As long as they're on your paper, you're going to be rewarded. All right. I have, with just a few minutes left, a very interesting problem here that you will all have possession of, that I just want to again give another homework assignment. Yeah, what is this guy? He's given us homework. We want Mr. Passwater back. He didn't give us homework. What the heck? So if you go to your problem that's contained within the 2000, I believe it's 2017, so we're going back 2 years. On the back page, we've got a part E with a star by it. And this particular part E was not on the operational exam this year, that particular year, but it was a question that was posed by the chief reader, Stephen Davis, back a couple of summers ago to kind of prep us for, what could happen with a L'Hopital's rule type of problem. So it's just basically an extension, if you will. And what I'm going to do is, because this problem doesn't have a scoring rubric, a scoring standard, I would challenge you to attack it much the same way that we attacked the previous problem. And I'm even going to write over here in the bottom right corner what the answer should be. What do you think about that? And I hope that's the right answer, because boy, I did this really fast. So Mr. P, if that is wrong, you please let me know. All right. So that's something that we can, you guys can take a look at, and maybe even in class, if you haven't discussed this, you can talk about that briefly. But what I wanted to finish up with is just a shade higher here, and it's problem D from that particular exam. So I'm going to unfortunately have to do a little bit of scrolling here, but the question reads, is there a number C on the interval -5 to -3 such that G prime of C is equal to -4? And of course, we are asked to justify our answer. So there's sort of this innate voice in some of your heads that sometimes will cry out, hey, this is looking like a theorem. Anytime that you have a particular question that starts with the words, is there a number C, it's very likely that this is not just a theorem, but more specifically an existence theorem. And we learn a lot of existence theorems in calculus. They're the ones that have the names like intermediate value theorem, extreme value theorem, mean value theorem. They basically say that something exists under certain conditions that are met. And that's exactly what's going on here. And if you can tell by the title of tonight's session, this is going to use the mean value theorem. Now, the mean value theorem, just in a nutshell, I'm going to write it in the box up here, is just basically saying that a derivative at a certain point is equivalent to the slope between 2 points that surround that particular point. Sometimes we can say that the slope of the tangent line is equal to the slope of the secant line. Now, of course, there's some other contingency values or factors here, and the fact that C has to lie between A and B and whatnot. So if we can just understand this structure, there's really nothing that's standing in our way to be successful with the mean value theorem problem. In fact, if you think of this equation of having two sides, the left side is already done for us, if you think about it. So if we know that G prime of C is going to equal -4 at some point, somewhere between -5 and -3, which isn't going to be very much, pen, please work, isn't going to be very much of this chart. So we have to think about, what is it? What kind of slope could we find that's going to give us this elusive -4? And if you just spend a moment and you look perhaps at these two values, okay, I can understand. I probably want to look at G of X values because I'm talking about the original function. And if I were to subtract those, 10 minus 2, and place those over the difference of the corresponding X values, I'm going to have 8 over -2. And that's equivalent to this -4. So we just need to kind of put that into a nice structure. So let's go ahead and we'll very quickly go to that chart initially, and we can say f of, doesn't matter where I start, so I'll start with -3 minus f of negative, or I'm going to start with -5 minus f of -3. And as I just said a moment ago, that's going to produce 10 minus 8 over -2, which of course is -4. Now, you've done something wonderful here. You've earned a point just by having that particular difference quotient, but we have to tie everything together, both on the front end and the back end. Let's talk about the front end. the mean value theorem cannot be used unless some very certain conditions are met. Now, I know that I didn't do a good job of introducing the stem of this problem, and that was basically because of time. But if you allow me to go back to the beginning of this question, it basically gives us every single variable in the world, right? F, G, H, we've got all of them here, it seems like. So the one that's kind of pertaining to this question would be the G. And it says that G is a differentiable function. And of course, the table shows the values of G and G prime. So that's all that we really have to focus on here. G is differentiable, but wait a minute. That's not all the conditions that must be met before we can apply the mean value theorem. Can you imagine what we're required to say now? And we would need to say that G is continuous. G is continuous. Now, I would be very careful throwing that phrase around, because when you say G is continuous, you're implying that G is continuous everywhere. And while that may very likely be true, I don't know if that's a can of worms that we want to open. So I would much prefer you to focus that in on the interval this time over which we're concerned. And that interval would be -5, -3. All right. Your textbook probably told you that you need to use closed brackets for the continuity. Mr. Passwater and I will tell you that that isn't quite a requirement because of the infamous parenthebracket. Have you ever seen one of these? That's a parenthebracket right there. Is it brackets? Is it parentheses? You know, we can't tell sometimes. So we're never going to scrutinize whether or not you're using the correct type of symbols, especially in a case like this. All right, so I'm going to go ahead and keep them as a closed, and I think that's going to take care of that initial sort of entry point into the mean value theorem. You would not have to say G is differentiable, therefore G is continuous, because the differentiability aspect is already part of the stem. But you do need to tie this together because we really haven't kind of grasped all the loose ends together. So we're going to say, you know, therefore, you know, G prime of C equals 4. That's a 4, guys. G prime of C is equal to 4 for some C on the interval -5 to -3. Okay, some C on the interval -5 to -3. All right, you do not have to mention the mean value theorem by name. I will tell you it's very powerful. If a student were to insert right here, therefore, by the, and please, I wouldn't write the whole thing out. MVT works for us. So by the mean value theorem, G prime of C is equal to 4 for some C on that open interval. If we go and look at the scoring rubric, what do we see? It's a good question. What do we see? That's D, isn't it? So we see that, yep, they went ahead and said that G is differentiable first, which implies that G is continuous, but that wasn't important. You could leave this out. You'd need that continuity aspect. Notice there's no points attached to that, but that is going to be sort of included indirectly with that second point. Here's your difference quotient. That's going to give you the -4, which is your first point. And then you just tie everything together. You tie everything together by saying that there is a C that does indeed exist. Now to finish up, I'm going to go ahead and assign another homework problem. All right, because I want to go ahead and cut the video short so that you guys can take a moment to ask some questions, because we know that this is probably the last time that you're going to be with all of us. I know you're going to have a few more days with your individual teachers, but hey, you've got both Mr. Passwater and myself in the room. So for this particular problem, the mean value theorem is actually part C. It's actually part C. And what I wanted to kind of illustrate here is just a different sort of level of derivative with which we're working. So if we read the stem here really quickly, it says we got a function f that's differentiable. Hey, guess what else is true, you guys? Can you imagine what would be a very appropriate thing to say down here? If f is differentiable, let's go ahead and say that f is continuous. Okay, if you want to really add that specificity, that specific continuity interval, maybe this would be a good one to state. So that would be your entry into this particular problem, that f is continuous on the interval 0 to 0.5. The only problem with this one is that you're finding a value of c. You're finding that particular c, not just showing that it exists, but you're finding it given the fact that f double prime of c is this particular value of r. Okay, so again, in the interest of time, I'm not going to assign this as homework because I've given you guys way too much homework tonight, right? This has a really low global mean, particularly because it's a very old problem. It's probably the oldest problem that we've worked together, but I really liked it. That's why I grabbed this. I don't really typically reach back that far, but I really liked it because it uses a different level of the derivative. And what I wanted to show you is that we use this particular setup for our difference quotient. We're going to use the difference of f prime now because we're working on, like I said, a slightly different level of derivative. So you guys hopefully still have your problem in front of you with the table and everything, but hopefully you can see that f prime of 0.5 minus f prime of 0 does give us a 3 value. And then if we subtract those two x's, we get 0.5, of course, and that yields 6, which happens to be that particular r that you're trying to find. Okay, it's kind of funny. Is it a c or is it an r? Well, the c is really where this particular value is occurring. The r is what the value is, if that makes a little bit of sense. Now, wait a minute. What's wrong with this? What's missing? What did they not write? I don't see the whole continuity statement. Well, that's 2002 for you, everybody. This is a problem that was written well before the redesign of 2017, so we did not hold students accountable for that statement that the function is continuous. But I promise, if you were to see a problem like this Tuesday, that probably MVT point here is certainly going to be tied to you saying that f is continuous, or f prime, I should say, is continuous on the interval negative or 0 to 1 point, or sorry, 0 to 0.5. All right, I can't write this. 0.5. All right. Hopefully that takes care of a few of these loose ends. Again, I apologize for having to jump around a little bit. This was a really challenging session to do. It wasn't nearly as easy as the other ones that I did that dealt with just simply running through one single topic and just moving through it like that. It was a little bit more helter-skelter because I had to kind of pull a lot of different problems from a lot of different exams and so forth. So with that, I am going to shut off the stream here. I'm going to stop the recording. Once again, I want to thank those of you from watching far and wide, and we hope that all of these sessions have been valuable, and we certainly feel that we're going to continue with these in the future next year, and maybe do them a little bit more commonly throughout the actual school year. But we want to say good luck to everybody out there on your AP exams, and go get them. Thanks.